the previous sessions, we have discussed the model parameter estimation for regression, that is based on two methods. One is least square estimate, and the second is maximum likelihood estimate. Now we are proceeding to a representational model for linear regression, right? So this representational model is nothing but how we are going to express the linear regression in some other terms. Why? Because we need to estimate the models, and always calculation need to be somewhat in a different approach always. Why? Because if there is only one way to calculate, then we may think that it may be complex. When there are two or more ways to calculate a particular estimate, then it will be easy to approach whenever a particular resource is available. Right now, we are going to represent the entire linear regression concept in matrix approach. That is, we call it as matrix approach to linear regression. Right. So this is actually a general form, that is y is equal to mx plus c plus an error term. We here describe here like beta naught plus beta 1 xi plus error I. Right. I'm having an error term here. Now the only thing to prove here is I'm not going into a multiple linear regression. Just a normal linear regression is available for me. And in spite of having a single independent variable, I can have any number of independent variables. Now I was in the previous stage before starting for the multiple linear regression. What I'm coming to say is I'm going to estimate my output to y with respect to different input values. So I name it xi. I can find y1 with respect to x1 with some error. And this, I can expect another different output with an estimate of x2. And I can estimate a different output with an independent variable xn. But the thing to understand here is I'm having a common gradient and common intercept. That is the thing to understand here. What is that is here? There is no different. I'm not taking any other consideration for independent variable. I'm just considering only one independent variable. Take it x1. So with respect to x1, I need to find some gradient and some intercept, that is beta naught and beta 1. Similarly, I have for y2 with some other independent variable x2, where beta naught and beta 1 serves as intercept and gradient respectively. The thing to understand here is, if I proceed to multiple linear regression, there should be a proof that x1 and x2 are independent. If x1 and x2 are independent, and I can actually directly proceed that to multiple linear regression, at that moment what happens? Y becomes equal to beta naught plus beta 1 x1 plus at that time I will put beta 2 x2. So because I want x1 and x2 to be modeled at the same time. This is one way when I go for multiple linear regression. When it is in the scalar form or in a linear regression way, I cannot put it like beta 2. Why? Because there is no estimate for x1 and x2 at the same time. So just I have a common beta, name it some other variable. Maybe it may, this beta 1 have a value here that can do an estimate for x1 for providing y. But the error term may differ. If I use x1, the error may differ. But for the same beta naught and beta 1, when I take x2, what is the error? For the same beta naught and beta 1, if I take xn, what is the error? These things I need to model and find. So this is the thing, right? And we have already seen that the most important point is the error is independent and normally distributed, right? When I say normal distribution, I say mean will be 0 and my variance will be sigma squared. And in more highest case, it will be uniform or uniform random variable, uniformly normally distributed. Where it happens is mean is equal to 0 and the standard deviation will be 1. But it is not possible in real time. So if it is happening, then it means that 100% my model is good, but that will not happen in real time. So we say that at least mean will be equal to 0 and variance will be some sigma squared, which need to be estimated. So this is actually the input models I have, and this is actually a separate linear line. Y2 is a separate linear line and yn is another separate linear line. So when I model these curves with respect to E, I should have a matrix representation for this. See, I have here y1, y2, dot 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 yn over here. That is all the same equations over here represented in matrix form. That is beta naught plus beta 1 x1 corresponding to y1, beta naught plus beta 1 x2 corresponding to y2. Similarly, beta naught plus beta 1 xn corresponding to yn. Each is the summation of an error term. That alone I take it separately. Why? Because these estimates of beta naught and beta 1 are going to be done by the minimization of sigma 1, that is the error term. With the minimization of the error term, I am going to estimate beta naught and beta 1. So I keep that separate. So what we need to understand is primary is, let us understand how the dimension are going on, right? Here the dimension is nothing but I'm having an n cross one dimension. I'm having n rows and one n cross one dimension is there, and this I'm having n cross two, and this is again an n cross one dimension, right? So this is actually the matrix representation of a simple linear regression. When I go for multiple independent variable analysis, I take all the variables into account, and for each of the independent variables, I'm going to do an analysis for estimating the y value. Now, what you're going to separate, I can take this beta naught and beta 1 separately out so that I can linearize this equation like it becomes 1x1, 1x2. Just multiply it using matrix 1x1. When I do a columnar multiplication over here, 1 into beta naught becomes beta naught plus beta 1 x1. Similarly, beta naught plus beta 1 x2 plus dot 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 beta naught plus beta 1 xn. So this is actually I'm just dividing this particular matrix into two and forming a multiplication oriented matrix, multiplication oriented form. So I'm making it here. So just taking it beta naught and beta 1 alone separate. Why I'm taking separately is these are the estimates what I'm going to take. So rather than keeping it in the input form, I just take it out and have a representation over here. This is a matrix representation form 2, where the initial matrix, that is, the initial equation is being converted into the matrix, and the matrix is now linearized using matrix multiplication. Next, now I'm having here a matrix here. This is actually the input what I originally have in my hand. Using this input, what I have to model is I need to get the values of beta naught and beta 1 in such a way that the error matrix is being decreased. So this is actually an n cross 2 matrix. All the values are available to me, right? That is the thing. And I already said, right? Usually when you see some machine learning books, especially Tom Mitchell book, this one constant one will be replaced by some values like x naught. Fully it will be x naught, because in the previous time itself I said, right, when I put the intercept term beta naught, it will be multiplied with another value called as x naught. Usually by default we will keep x naught as 1, so I will be directly having beta naught alone. So the x naught value will be remaining as 1 itself. So all the x naught values remains 1. So you can substitute either x naught here, or you can directly put 1 over here. So this is the thing. Next, coming to the next parameter, the parameter what I'm going to estimate, that is the intercept term and the gradient. These two terms I'm going to estimate, and I call that as beta, and it is going to be a 2 cross 1 matrix, right? Next, I have an error term over here, right? This error term are also obtained when I finish my regression values, and these error terms should be minimized to find the beta naught and beta 1 values. This error matrix will be a n cross 1 matrix, and I name it sigma. Coming to the final, the response outputs. I'm going to have an value y, which is going to be an n cross 1 matrix, and all the variables are enumerated like this, right? So we have a representation like that. So what is my ultimate aim? What I'm going to do is I'm just going to write it as y is equal to beta naught plus beta 1 x plus sigma. Like that I'm going to write. So what I'm writing, y corresponds to y1, y2, dot dot dot, yn, x, etc. And x, the n cross 2 matrix, 1x1, 1x2, 1x3, dot dot dot, 1xn. Everything is actually available here. And beta is nothing but beta naught and beta 1 will be the matrix plus the error matrix. So this is actually a simple linear regression in a matrix form, right? So far so good. Actually simple representation, right? So far so good, students. Am I going good?
Yes, sir.
Yes, sir.
Yes, sir. Thank you. So just I'm having the dimensions over here. So the point of understanding here is just if I ask for like a question, I give you a table of values, and if I ask you to calculate the regression for each table, you cannot do the regression and find the values. Instead, you can just substitute in the matrix and then get the result. That is the thing. I'll also give you an example, and you can solve it. Now, this is actually the next matrix. What I'm going to do, and this matrix will be the beginning to understand whether I should proceed for multiple linear regression or not. So what is this is the covariance matrix, right? I'm having y, and there should be a correlation between the y values. How the correlation will obtain is when two y values are depending, it means that those two equations are actually having some characteristics. Example, if I say y1 is equal to beta naught plus beta 1 x1 and another y4 is equal to beta naught plus beta 1 x4, if this y1 and y4 is going to have some covariance, means that their values are somewhere related. It will be like saying like 4 is equal to if I, for example, if I want to say an equation 5 is equal to 2 plus 3, that will be the y1 equation. Y4 equation can be 10 is equal to 4 plus 6. Then so both equations are having some same characteristics. Let me enumerate, like I write like I'm saying again, if I say write like 5 is equal to 2 plus 3, 2 plus 3 is 5. Assume that as equation 1. Say for that equation is obtained from y1. I'm having another equation, say 10 is equal to 4 plus 6. So actually, it is actually the double of equation 1. If I have some characteristics between those y1 and y4, it means that those equations are not significantly equal. Any one of those two can be taken. So what is my ultimate aim? There should not be any covariance between the y values. If though that covariance doesn't exist, then I can proceed to take both the independent variables contributing for that corresponding y values. Otherwise, I should not take the x4 and x1 together. Any one of x1 or x4 I should take. So that's what I come in here. So I take all the y values. So this is actually in the matrix form, enumerated like y1, y2, and actually I'm taking the variance of all the y values. This diagonal is nothing but the covariance of y1 by itself, right? So this will be actually exactly one. So the mean will be the main diagonal matrix will be exactly one because covariance of y with respect to itself will be same. But the other terms, if it is equal to 0, then it is great. If it is equal to 0, then the covariance matrix is good, and we can actually go for the multiple linear regression containing all the independent variables. If the other variables are not equal to 0, at least their covariance should be as low as possible. That is the variance or standard deviation, the variance between sigma y1 and y2 should be as low as possible, and variance between y1 to yn should be as low as possible, and so on, right? Now another thing is, this value is also exactly symmetric. What are the values you obtain on top will obtain on bottom also. So it is actually symmetric. Y2 to y1, y1 to y2, it is they are symmetric, and they can estimate any one of the two. Similarly, the covariance matrix of the error terms, right? This error covariance is also most important. Why? Because if for a particular independent variable, say x1, you are calculating the corresponding y1 value, and if for another error value, say e4, you are calculating another response variable y2. If the error is actually mostly same or actually very close, then it means that for either for x1 and x2 the error is same. Then why I have to take another different value? Because for both it is actually contributing them as exactly some same values. Then there is no need of taking both x1 and x4. Any one of x1 and x4 can be taken. So another condition what we state is the error should be completely independent. That is, when I take the covariance between error 1 and error 2, the covariance should be equal to 0. There should not be any variance values. Or simply I should have to say that it should be a sigma squared and an independent matrix, so that there is no covariance available, right? The diagonal value should be exactly 1, and all other off diagonal values, that is except the main diagonal, all the other elements should have the covariance of 0. If it is like that, then it is proven that all the error values are independent. I can take all the independent variable for analysis. So this is the second one. Next, I can also do the same thing for analyzing the response variable. Right, this response variable, if it was equal to sigma squared I, means that all the matrix are actually equal to 1. Means that the variance between yn and y2 are equal to 1. The variance between y1 to y3 is equal to 1. Y1 to y4, everything is equal to 1. Means that all the from y1 to yn, everything are actually dependent on each other and having a covariance of 1, everything are same. Then it is mean that it is a pure simple linear regression, and we need not go for multiple linear regression because everything are equal to 1. Same thing what I said here. If some sigma 1 and sigma 2, sigma 1 and sigma 3, everything are actually giving the same value equal to 1. Just I can put an identity matrix over here and say all of them are actually having the same variance. So I need not go for the multiple linear regression itself. It is a pure simple linear regression. Now, the thing to understand here is that we have already dealt here. Now we are going to apply the least square estimate for analyzing the beta naught and beta 1 values in the matrix notation. Right? That's what I said here. So yeah, I said I had an assumption here that error will be normally distributed and will be equal to mean will be equal to 0 and variance will be equal to sigma squared I. How this sigma squared I came? We understood that all the error values are actually having the variance equal to 1, and it will not be independent. It will be independent purely, right? When I have an huge number of independent variables, all the independent variables do not have any characteristics between them, right? And once in the diagonal element specify that the variance between the element and itself be equal to 1. That is, if I take variance of x to x, then it means that both will be equal to 1. And the off diagonal elements is nothing but other than the main diagonal elements, all the other elements, if they are equal to 0, then it means that all the errors are purely independent and all the error values are equal to 0. The correlation between all the error values will be equal to 0. And here comes the least square estimate. I take y minus x beta dash and y minus x beta, nothing but the error squared. The error value e can be represented as y minus x beta, and I can, if I want to take sum of squares, I can just take y minus x beta dash into y minus x beta. This derivation we have already seen in the least square estimate, and the same thing is depicted here. All the same values will be coming, and hope you remember this formula. I can estimate the beta value as x dash x the whole inverse into x dash y. So this is the value what we actually obtained by using the least square estimate. We had a derivation for this and proved this, right? And that's what we said here, right? We'll directly come onto the final one. Yes, here. So if I was saying that y cap value is going to be x into that, instead of beta, I can write as x dash x the whole inverse into x dash y. Hope you remember this. X dash x the whole inverse into x dash y is the estimate for beta 1 obtained by using the least square estimate, right? So I just multiply it with x to find the predicted y value. Now we can have a representation for this. This y cap is going to be the predicted y value, and this y is the actual output response variable. Like other than that, I have x into x dash x the whole inverse into x dash. This and all the terms I can denote as hy, and this H is called as hat matrix. I repeat, it is this H is called as hat matrix. So I just take that hat matrix out and I say that x into x dash x the whole inverse x dash, right? And this hat matrix has various features, meaning that whatever variable that comes in the hat matrix are purely symmetric, independent, and they will have a proper correlation relation, right? So what is the proper correlation is, if a variable should be taken. For example, if I find the correlation between x and x dash, all the variables are same. X dash is nothing but the transpose of x, and I'm just taking the inverse and then I am actually calculating. There is no other variables involved. The features of hat matrix, first I said is they will be symmetric. That is, either I can do x into x dash or x dash into x, because every x are actually a matrix notation, and that is and in the correlation is also same. That is means that now none of the other variables will be involved. Only the same variables will be involved. X, and x. All the x, only x variable is involved, and none of the other variables will be involved in the hat matrix. HAT. This is called as hat matrix, right? When using this hat matrix, if you have any number of independent variables also, if you say that I have x1, x2, large number of x values also, you can easily determine. So why we take this hat matrix alone separate is, here we estimated the value of B is nothing but the beta 1. Beta 1 value alone we estimated, and then we calculated the hat matrix. But when you go for multiple linear regression, each of the x value will have x1, x2, dot, 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 xn, and so on. So all the x value will have many forms. So I need not consider that I need to find another estimate for this. Just I can use this matrix notation and substitute the x values over here and then find the result. So this hat matrix is useful when even though I derive the estimate for linear regression, I can use the similar estimate for the multiple linear regression with an assumption that all the independent variables are checked before going for multiple linear regression. And the word checked means that there is no pattern between the independent variables, right? So this is the thing. That's what I know. This matrix B is a linear combination of all the elements of Y, and these estimates are normal if Y is normal. So everything is actually coincide with the output variable Y, right? This estimated will be approximately normal in general, right? But ideal notation is there will be uniform normal, means that mean will be 0 and the standard deviation will be equivalent to 1, right? So the matrix notation is this. So what is the ultimate is when I give you a table of notations. For example, if I give you x1, x2, dot 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 x something, and if I ask you to estimate beta naught and beta 1, then you should be in a position to easily apply it in the matrix and find the results of y1, y2, dot 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 yn. Immediately you need to be doing. But because if you assume that if I give you a table for x1, and if you are estimating for x1 separately, then x2 separately, then xn, then you are actually drawing a line, then it will be a very big problem. But when you do it in a matrix, the problem can be done very quickly, right? Is it clear? And I'll just have a recap over here. Just these equations are represented as matrix, nothing more, right? When I convert into matrix notation also, I'm again using the least square estimate only, right? Just having this notation y is equal to beta naught plus beta 1 x1 plus e1. And the same thing I'm using and then forming into a matrix. How am I forming a matrix? This particular notation. This is actually the matrix what I'm actually forming. And then I'm saying that y is equal to x beta plus sigma, right? This is a notation what I'm trying to bring. Let me share. Hope my another screen is also visible.
Only one is visible, sir.
Okay, okay. Let me share it. Let me share the entire screen. Now we have completed the least square estimate, maximum likelihood, and the matrix representation for linear regression. So what I'll do that now I'm showing you the IBM PPT here. So just we can have a recap. Here it is everything is given like an abstract term, not an very big derivations are not available here. I will post those derivations what I have did during the class in our Google Classroom. Okay. So this is the thing. We are actually in this unit we are coming across the supervised linear regression modeling, and all are actually deterministic. We are not going into the stochastic versions, just having a deterministic model. Checking like I'm just giving that supervised learning diagram. Hope you know that here if labels are available, it means that the machine learning algorithms are documented over here. If the labels are available, it means that the machine learning algorithm will be taking place over here. Whatever documents are shown, whatever input use case you are taking, the features are derived, and along with those features, I have the labels also available and give it to a machine learning algorithm. When labels are available, it means that giving a supervision to my machine learning algorithm, and my algorithm will do an analysis over it. Now, during testing, when I get a new text or image or sound, and the similar features as done in the training will be obtained here, and model analytics will be taking place over here, and I'll get an expected label, right? For example, if for this particular feature I'm getting the label 1, then for this particular feature, what will be the label, right? That will be analyzed, and the expected label will be posed here, right? So that's I'll having a training data and develop one model, a learning algorithm, and this model will be subjected to a test data, and and an accuracy will be derived. If the accuracy is not close to 100%, I need to remodel it again, or I need to vary my parameters, right? So I say the accuracy is going to be number of correct classifications divided by number of test cases I take. For each number of test case, how many number of times it is correctly classifying and how many number of times it is wrongly classifying. Right now, coming into the regression, but when I just revising it, why? Because we already seen these regression themes, right? I'm having an independent variable, I call it x, and a dependent variable or a response variable y. This output variable will be depending on an x, and you can do this analysis only when I experience a linear characteristic between y and x. If there exists a linear characteristic between y and x, then I say that they are actually linearly related, and I can perform a regression over those pairs. Examples of regression, I can say it as a sales price detection, or using machine learning you can predict who will be the next wicket in the cricket match. You can actually forecast the rain, and that's weather forecasting. Many things you can actually do by using the regression. If you see this, everything what I say, whether it is a sales price, selling price, or whether it is showing a cricket match prediction or weather prediction, everything is actually dependent on the historical data. So regression by default means that if my historical data is not perfect, then I cannot go for regression. Only when I have a good number of data available, I can actually use those knowledge in my model and then do some prediction on the new questions that arise. So these regression models can be either simple or multiple. Right? When I go for a simple, I have a linear regression and a non-linear regression. This non-linear regression is nothing but curve. Like one time Yogender said, right? We can have a parabola also. And I do a regression. Right? Now, this parabola means that I'm trying to fit the lines as close as possible. Right? But we should be very clear that it should not overfit the line also. And next is multiple regression. In multiple also, I can have a linear and a non-linear. Right? To bring the non-linearity to a linear form, I use some kernel terms and so on, which will be seeing quite next classes. Right? So the steps which we'll be using in the regression is nothing but I will be having some problem. I'll be having the labels, right? I'll have relevant variables and what will be the independent variable and what will be the dependent variable. Everything I'll be having with a huge support of historical data. So once the relevant variables are supported by historical data, I can use the knowledge from the historical data and build a model. Once the model is built, I can actually try to fit my training data in the model. But I should be very careful that when I was fitting the model, it should not exactly fit my training data. So when it is mugging all the data, then when a new data is coming, it may not predict the value more appropriate. So it may go for some errors. So that I can identify, and then I can rectify those overfitting things by using some cross validation techniques and error minimization techniques. Or I mean by error minimization, I say the gradient change. I can change the parameters and then I can estimate again. Now coming to the linear regression. So the regression is nothing but the independent the relationship between the independent variable and the dependent variable. The independent variables are those values which are actually used to predict the output value. The output value can be either a boolean value, say 0 or 1, or there can be a continuous value like some age or something, or it can be like weather forecasting values, temperature values, or anything. It can be either nominal, ordinal, or boolean values. So these dependent variables, by when I say it was discrete, I can actually orient it to something called as classification. When this independent variable is going to be continuous, I can say it for regression, right? So that's what we will be doing, right? When I was modeling a continuous variable, I go for regression, and when I was modeling a discrete variable, I go for classification, right? So when I was actually doing with a continuous y values, I can have the pattern over here. For example, we have a huge number of points over here. I exhibit a linear orientation over this. I can just draw a line over here in such a way that the line actually is closely aligned to maximum number of points, or the total error is minimized. But if I exhibit a line like this is actually not linearly related. This is non-linear. Uh, Perfectly a parabola can fit, but I cannot exhibit a linear line for this because if I try to fit it with a linear line, surely I'll get a large amount of error. So surely I cannot do that. So if only when a linear pattern is available between two variables, I was actually subjected to a linear regression model. Otherwise, I cannot use the linear regression model. Now, coming to the simple linear regression, I have y. The y value can be either equal to beta naught plus beta 1 x plus sigma. This beta naught and beta 1 I say the parameters to be estimated for the given linear model. How this parameter need to be estimated is this parameter should be estimated in such a way that error is minimized. My error term is sigma, and for each time my model is executing, it will surely have some error. In ideal case, we'll try to bring it to zero, but which is not possible in real time. Beta naught is nothing but the intercept term, and we will also call it as a bias term. And beta 1, we call it as the gradient or slope or the weighted parameter for the independent variable. Right? Once, and I can also call it as a regression coefficient. Now, how we are going to estimate this y value is going to be the next thing, right? Now I can actually take how the y is going to have. Like I can take the expected value of y. When I take the expectation for y, the expectation of y is actually obtained from beta naught and beta 1 only. Only when y is obtained and I go for the actual minus predicted value, I can find sigma. So the expected value of y will not depend on sigma. Why? Because sigma is actually obtained when I do y minus y cap. When I do y minus y cap is nothing but the predicted y value. At the time only I can understand what is sigma. So the expected value of y will be depending only on this intercept and slope and an independent variable x. And the variance of y I just name it as sigma square. So whenever we go for the parameter estimation, we calculate beta naught, beta 1 and also the variance. So only during the least square estimate and the maximum likelihood estimate, we also estimated the variance, how the y is actually varying with respect to the input. Now coming to the least square estimate, I'm having a linear line over here, and once the linear line is available with respect to the independent variable x, how the beta naught and beta 1 values are estimated, right? That's what we are actually doing in least square estimate. Assuming that y is equal to beta naught plus beta 1 x, I need to take the error term out. So I can take the error term as y minus beta 1 x. That's what we actually did in linear regression, and it will be available here. So, say for example, is hours of sunshine and by ice cream sold, right? Based on the sunshine, the number of ice cream sold will be predicted, right? So, I'm having an x variable and a y variable. How many ice creams are sold with respect to the hours of sunshine? If there are sun for 2 hours, 4 ice cream is sold. It is when it is 3, 5, and when it is 5 and 7, and so on. So we say that y is going to depend on x, and we can actually model a linear curve for this x and y, and model it as y is equal to mx plus b. With respect to this thing, I can actually take it the name estimation what I did in Paint window and Word screen is actually given here in some abstract manner alone. But the detailed version I have given separately. We will also post that on our Google Class, right? They have depicted here y is equal to beta naught plus beta 1 x plus sigma I, where the estimated parameters, right, should be in such a way that it should minimize the sum of square errors. By base sum of square errors only, my beta naught and beta 1 errors should be calculated. So this say, sigma I squared can be calculated as yi minus beta naught minus beta 1 xi the whole square. So just taking this beta naught and beta 1 xi over to the left, and I take yi minus beta naught minus beta 1 xi the whole square. So taking the partial derivation, and we did this right. When I take the partial derivation with respect to beta naught, I can estimate the beta naught value, equalizing it to 0. Similarly, I take partial derivation with respect to beta 1 and equalize it to 0. Right? And then based on that, I estimate the parameters beta naught and beta 1. And this estimate is with respect to the minimization of sigma only when the second partial derivation is a positive value. Right? We also proved that it is a positive value. Similar estimate, the very big equation what I did for maximum likelihood estimate is given in a single slide here. I have that also to you. How I'm taking the normal distribution curve over here. This is actually the normal distribution term, right? Using this estimate, we derive with respect to beta 1 sigma squared, and estimate it separately. So there are two number of estimates, either using the least square estimate and the maximum likelihood estimate. And this is the matrix notation, right? I say that how the matrix notation will be done. So here also it was given more abstractly. The detailed version I have it in my own PPT. I'll also share it. Right now you have understood the thing, right? We have come across the regression terms and the model estimated parameters by using two techniques, that is least square estimate and maximum likelihood estimate, and the matrix approach for representing the regression terms.